All, my name is Dave Sebastian. It's great to see you all. And we love to see our customers, and today is no exception. It's wonderful to see you all. Thank you very much. So here I've got a PowerPoint presentation. This will just let you know what we're going to cover in this webinar. First of all, it's about the spray sprinkler module. We will cover both basic and advanced topics. And if you have experience of PIPENET, please bear with us because there are people here who have never used PIPENET, and we need to cater for their needs as well. And even if you're an experienced user, you may learn something from the basic principles I'm going to be talking about today. And if you're a new user, you will get an idea of how powerful PIPENET is. So let's have a look at, in more detail, what topics we're going to cover. So this is part 1A, which is the first part of the basic principles and is concerned with deluge system calculations. And it's what I'm going to be covering today is how to create a pipe schedule in the library, how to create nozzles, how to input a simple network, what is meant by the most remote nozzle option, and then if there isn't enough pressure at the inlet of the deluge system, are there any options that we have for checking what we need to do in order to get the system to work properly? And then, of course, I'll cover the case where the inlet pressure is too high and what we need to do about it. In the olden days, I'm talking about 25 years ago or something like that, people just used to check that the 5-watt ringmain generates enough pressure and that is enough. But in fact, it's not enough, because if the inlet pressure is higher than necessary, the deluge system will discharge too much water, and that ultimately could result in the need for a fire pump that's bigger, or if you're using a tank, the tank emptying too quickly. So you mustn't simply stop because the inlet pressure is too high. And I'll cover the use of restriction orifice plates and elastomeric valve. And we'll also show you a bit about how you can input a network quickly. So that is about deluge systems. And part 1A, 1B, the basic principles of ringmain calculations. And I'll cover clack valves, debottlenecking the system, and how to model elastomeric valves, rules concerned with specifications, blocking a pipe, moving a pipe, how to select pump, using booster pumps, and modeling tanks. These are the items I will cover regarding fire-water ringmains. And then part 2, this is for more advanced users, how to create a great story in the design process. When I say great story, I don't mean fiction. I mean, in the design process, how would you go about optimizing the system? Because at the end of the day, the engineering company and the operating company have a common purpose, which is to optimize the system. That's the first purpose. And the second purpose is to analyze the optimum system to see how it'll behave under failure conditions. So that's what this is about. I will also cover how to combine subnetworks and balance a system. In a minute, I'll show you a very large network, and that was created by combining subnetworks. And break in the sense of a pipe rupturing, and how to use that in an offshore system, why it has a certain purpose in offshore systems, and we'll have a look at that in a little bit more detail. A methodology that's developed over a long period of time is to use the virtual nozzle to represent a deluge system. I will show you why that evolved. I will also point out when you must not use that methodology. That methodology is very useful and it makes life easier for us, but there are circumstances in which you must not use that methodology. First of all, the rules regarding specifications. I'll very quickly explain what they are. Basically, the number of inputs and outputs is equal to the number of pressures plus the number of flows. And that is the number of degrees of freedom. And so you must take up the number of degrees of freedom by giving exactly the right number of specifications. So if you have a system with 5 inputs and 3 outputs, total number is 8, so you need to give 8 specifications. There must be at least one pressure. It's obvious, because if PIPENET doesn't know the pressure at any node, the pressures at the nodes can be freely floating up and down. So you need to anchor the pressure at some point in the system. So there must be at least one pressure specification. So that actually is these are the 2 basic rules, and I'll explain a little bit about how to interpret them later on. So let's go on to that. This is the large system I was talking about, which is built by combining subnetworks. You can see the system has more than 9,300 pipes, more than 13,000 nodes, and just under 4,000 nozzles. It really is a big system, and it makes it convenient to be able to combine the subsystems to build this system. There are 2 reasons for that. One is if you have a system like this is actually from a gas field, and they tend to have several platforms, and the fire pumps may be starting on one platform, but the fire may be on another platform. So with this, you can show clearly what will happen under such circumstances. That's the first reason why it's a good idea to build a system like this. You see, you can do this even if there are different subcontractors working on one project, and different people are creating the different deluge systems. So you can combine them, or you may have a part of the system that's been defined before, earlier on, and you may be wanting to add another platform to the complex, in which case you can simply you can optimize the deluge systems on the new platform, but you can combine that with the existing large system. So that is one reason to be able to perform the calculations more accurately. And the other reason is that for the operating company to have a record of the complete system is beneficial. If we have the data files for all the deluge systems and the firewall ringmain, then you will have a very, very large number of data files. You must archive them, but it's not convenient to go hunting around for the right set of data files. Later on, when you want to retrieve something from the archives. In fact, what you can do is to select a system from here and then copy and paste it into a system in which there's nothing, and so you can actually have the system on its own and do calculations later on if you want it, if you modify it. So you can extract components in this large system and work on them separately if you want. That's the reason for developing this very, very large system, which is complete, and you can do that by combining subsystems. You must be organized because you can see that they're all in different orientations, and it's a good idea to start with inputting the subsystems in such a way that they easily fit into this combined system. Okay, let's start with the basic principles of how to input a simple deluge system. Start the spray module. You can see it's got grids. I can switch the grids on and off. I can have orthogonal grids or isometric grids. And there are 4 windows here, and this is called the schematic overview. That's the schematic area, drawing area. That is the properties window, and that's called the data window. You may find that your desktop looks like that, but you can bring up the windows by going to view, and in fact it may look like that because that's what Windows does. It puts it where it wants to, and we can then combine this. We must activate it because I find it more convenient to work with the schematic at the top. So this is a drawing area. And there are shortcut tools here, and these are the tools with which you can build the network. You can see that the pipe tool is actually grayed out. Now that's because until you choose a pipe schedule, PIPENET will not allow you to input the network. Okay, let's start. Options. I'll just say demo. You can put some text here. Module options. I will not go into great detail here because we haven't got time. But I'll just mention a few salient points. The first one is pipe elevations and node elevations. Pipe elevations is more common. That is the elevation difference between the input node of a pipe and the output node of a pipe, and it's positive if the pipe is going up, it's negative if the pipe is going down. And the reason why it's more common is because most pipes are horizontal, so you can default the elevation change to 0. On the other hand, if you're working with an isometric, it will show you the node elevations with reference to a datum. So you can simply take those values and put them in here. It's up to you. You can also interchange between the two. And I'll just mention the crane option is the more common option, but these two are flow metering orifice plates, and that's for the restriction orifice plate. And PIPENET can also model, let's say, foam concentrate, in which case you will choose Darcy equation and specify the properties of the concentrate here. Units is very important because there are people from North America. I will mention that because in North America, especially in the United States, some people use what are called English units, and that's GPM and PSI, an inch for pipe diameter, and so on. You can freely switch between the units. So if you're a company based in the US and you're more comfortable with English units and you have a subcontractor who is in another country and they prefer to work in metric units, then also many engineering companies in the US and in North America are multinational companies. So you may have a subsidiary which is doing the calculations for you, and they may prefer to work in metric units. And our recommendation is always work in the units you're familiar with, because you're less liable to make mistakes. Having done that, you're not stuck with metric units, because the operating company or a company in the US may prefer to have all the data files and the results in English units. And if you want to change, you can change. You must change to US units. Don't change it to British, because it's very similar to English. You must change to US because a US gallon is different from a British gallon. And so you must choose this. Now, I prefer to work with metric units if you don't mind. But the important thing for you to recognize is that you can actually do the fine tuning in metric units, but have all the data files and the report and the results in English units. So metric units, let's say I want to basically work with metric units, but the diameter, I want to use inches. So I choose metric, go to use a defined, I'm going to copy diameter. So you can see the units. I can choose inch if I wanted to. In that way, I can have the actual combination I want. There are some countries where kilogram force is more common than bar. So you can change to kilogram force as well. So I'll go back to metric. And pipe types. What is a pipe type? Pipe type is the pipe schedule which you're going to use in this network. One thing I would like to add is that you can have up to 10 pipe types in a single network. 10 may seem a lot, but in fact, we used to have a limit of 5, and a few years ago, a Norwegian engineering companies told us, hey, we got some old systems we're working on, and we're going to exceed the limit of 5 pipe types. That's why we increased it to 10. So if you have older installations, you may find that you have several pipe schedules in your system, or it may be that some of your pipe schedules are lined, and if you have lining, you have to treat it differently from an unlined pipe. So that's what a pipe type is. It's the choice of the pipe schedule you're going to be using, plus some additional data. So what I'll do at the moment here, I'll take a break, click on OK, and then go to the libraries and show you how to create a pipe schedule. That's what I'm doing, and then I can click on New. Got fiberglass. I've got to input the ID B. Make sure that you input the actual ID here. Don't just input the nominal size. I'm putting in some random numbers here. So I'm putting the pipe sizes, nominal sizes that I think I'm going to use in this system. So I can apply, and it goes here. Go to nozzles. I want to now add some nozzles. The K factor is 45. Minimum pressure is 1, and the maximum pressure is 10. These two values are actually not used in the calculation. That's here simply for diagnostic purposes, because your nozzle vendor would tell you the minimum and the maximum recommended pressures for the nozzles. And if a nozzle works outside this range, PIPENET will produce a diagnostic. What's the spray divergence angle? As optional input. I will not input this here. PIPENET has a feature called auto layout. Unfortunately, we will not have time to cover that today. Maybe we can cover it in later on in another session. But if you're, for example, developing a deluge system for a tank or a general area protection, then there is enough guidelines in the NFPA rules to be able to generate networks automatically. For example, if you've got a vertical cylindrical tank, the basic rule is that on the horizontal plane, the ellipse of impact, they must at least touch each other. It's healthy to have an overlap, but they must at least touch each other. On the vertical plane, you can rely on the rundown, and so the distance between the rings is recommended in the NFPA rules. So using those, you can automatically generate the network. To do that manually actually is very time consuming. So just to do the estimation is very, very useful. The auto layout can also show the spray pattern on the tank. That is also very useful. There are operating companies which do not follow strictly the guidelines in the NFPA rules. For example, certain oil companies say that they will just have one ring at the top of the tank, and they will rely on the rundown for the rest of the tank. And you can do that in PIPENET. And so that's what this is. I will not input that here because I'm not going to show the auto layout feature today. Apply, new. So input that, I click on OK. Having created the library, I'm going to save that. I'm going to go to the webinar directory. I'm going to call it, say, demo 2. Now let's save it. Now, if I go to the webinar material, you can see that there are 2 files, demo 2 and demo. And this is the SDF file, and that is the SLF file. So when you request support from us, do remember to send both files. Because if you just send us the SDF file, we will not be able to open the SLF file, the data in the SLF file. What is the SLF file? It's the information I input into the library. So why does PIPENET 2 create 2 files? It's because I can go to File and import the library. It's a very useful feature because if there are a number of people working on a project, which is more and more common these days, and if you can import the data files, not the SDF, the SLF data file, the library file. I won't import it because the data is already in the library, but if I click on that, you can see that the name appears and you can open that. So you can share a library in the project or one system, or even for a company, because if you are a company using the same nozzles and the same pipe schedules all the time, you may not wish to create a library every time. You may just create a read-only library and then keep using that. So let's go back to these options. Now you can work with the pull-down menu or the tabs. So we'll go and choose a pipe schedule. See, let's put 140. So if you've got line pipes, for example, if you've got an onshore plant such as a refinery, it's conceivable that you have lined pipes. I won't use that in this. Maximum velocity, let's put 6. I want to assign 6 to all of them. I can input them one by one. Alternatively, I can click on that, click and hold the left button and drag it down. Then apply. Now you can see that has become active now because I've chosen a pipe schedule. I can maximize this because I want to input the network. Click, very, very simple. Click, and I want to create a waypoint here. Press and hold the shift button, and every time I click, oops, my shift button is actually broken, so it doesn't always register. So let me start again. Press and hold the shift button, click, click, and then I want to create a node here. I'll release the shift button and click. So you've got your pipe. And click, 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 click. It's very, very simple. So having created the network, I can hang the nozzles, pick up the nozzle, click, click. So if I want, I could actually, oops, let me hang the nozzles here. I can copy right click. See, I'm using the area tool to select part of the network, right click, paste. So I can move it there and then work with that. I can put a connecting pipe. Now in this way, I can create the network very quickly. If I've input the attributes of the items here, then the attributes will also be copied here. I can undo. Don't undo too quickly because the database needs to have a little bit of time to refresh. So do it a little bit slowly. So you can see that if I click on a blank area, everything is blue. Blue indicates that I have not input the attributes for the item or the minimum attributes. If I click on an item, it becomes red, and the attributes of the item are shown here. It's also highlighted in the schematic overview. If I have the properties window, it's also selected here. So let me show you a very quick way. See, the pipes schedule I've shown is here. You can see that I'm not a brilliant typist, so it's I meant to type GRP, but some other characters have appeared here. So I'm going to say 25, click, click, right click, copy, right click, and paste. The length, I'm going to input 5. Paste. Now, if I go and click on that, you can see that all the pipes are black. It means that I've input the attributes of all the pipes here. Okay, and it doesn't mean I've input complete information. I've input the minimum required attributes. I can switch off the grid. For example, if I click on that, there are 2 elbows here. I can add the elbows by going to this tab, choose that, and add it twice, and you'll get 2 elbows. One thing I could do, see, having done this, I can actually modify. And then I can go to that elbow and add 4 more elbows, making a total of 6. Sometimes people ask, why can't you count the number of elbows? This is a schematic drawing. It's not a scale isometric. The 2 reasons why it's not a scale isometric. If it's a scale isometric, you've got to input all the items, all the fittings and everything, and draw the network to scale. And that will take you a very, very long time. And that's the first reason. The second reason is it only takes one very long pipe somewhere in the system, and everything else will get bunched up together if you do the drawing to scale. So that's why it's a schematic. It's the easiest way, because engineers' time is very expensive and they're not in the job of importing drawings like this to scale. In fact, this historically, this comes from what used to be called hydraulic isometric. People don't do that anymore because it's very easy to draw the hydraulic isometric in PIPENET. You can, this is good enough. You know, some people even use this for fabrication. So it is, in any case, a schematic, and there are good reasons why it is a schematic. So I can go to the nozzles. I'll save that. So go there. By the way, there's also an autosave facility somewhere along here. That's grayed out because I've just saved it. But autosave will enable you to save every 10 minutes or something like that. So if for some reason there's a problem with your laptop and it ceases to work or something like that, you've only lost 10 minutes of data. But you've got to remember that if you want to keep a file for permanently, then you must save it with a different file name, because otherwise it'll get overwritten. So that's the save. Do a save. Nozzles. Choose high velocity, medium velocity nozzle. Copy. Paste. It's more common to work with the required flow rate for each nozzle nowadays, and click on that. Click. Copy. And paste. So now we can see that not only the pipes, all the attributes of all the nozzles have also been defined. So a question arises, what is the very first calculation I will do? The first calculation I will do is called the most remote nozzle calculation. Okay, for that, I will simply define the input node as the input. That's all we'll do, because I would want PIPENET to calculate the pressure and the flow rate here. I will not give the specifications. Let's cast our mind back to the rules regarding specification I mentioned there. If there's one input, there's 1 degree of freedom. So why am I not specifying anything? Because I'm going to specify the most remote nozzle option here. Once I choose the most remote nozzle option, PIPENET will select the worst nozzle in the system, hydraulically most remote nozzle, and set the flow rate there to be equal to the minimum flow rate. So there is a specification. The rule is satisfied, but the specification is set by PIPENET, and it can estimate the most remote nozzle. What about pressure? We said there must be at least one pressure. The outlet pressure of every nozzle is set to 0 bar gauge or 0 psig by PIPENET by itself. The user doesn't set it, and hence there are pressures specified at the outlets of all the nozzles. So that's why when you define the select the most remote nozzle option, you don't have to give any specifications. Do the calculation. You can see how quickly you do the calculation is instantaneous. You know, even that very large system that I showed took only 10 seconds to do the calculation. what actually takes time is the output of that onto the disk. Even solid state disks take a very long time because I/O of data is still very slow in comparison to the CPU. That's why I didn't run it. Anyway, we done the calculation. Let's look at the first thing, of course, you would look at the input node and look at the pressure and flow rate. I'm going to make a note of that. It's 8.43307 and the flow rate is 394.1. See, for such a small system with 6 nozzles, that pressure is very high. In fact, if you interested to know what it is in GPM and PSI, see 122 PSI for such a small system is wrong. But it tells me that something is wrong. So I want to debottleneck. I can look at the pressure differences along the pipes. I can see that it's showing the pressure drop in every straight section. I don't want that. So I can go to options. I can remove it by going here. See, you got 5.8 bar. That's almost 90 PSI. Most of the pressure drop in this is in this line. So I want to look at the velocities to see what's wrong. If I go to US units, it's 45 feet per second. It's very high. So it's clear that I must increase the size of that pipe. I can make it 40. I'll tell you what, let me reduce the noise to so that you don't keep getting that ping on your speakers. So I'll just click on that. Please come right down. You know, the velocity is quite reasonable. Look at the pressure drops. I can increase that if I wanted to. It's still a little bit high, but don't forget that there is a static head loss here. So I'm going to make a note of that. But you see, the flow rate is the same as before because changing the diameter of this pipe doesn't alter the pressure loss characteristics here. So that's why the total flow rate is the same, even though the pressure goes down. So I make a note of that, 3.672825. The flow rate is 394.1. So I said, you know, the next topic I wanted to cover is what can we do if the pressure here is a little bit low? The first thing I'd want to do is to see, is that a problem? User defined, because it's not the most remote nozzle option. Let's say I want to give a pressure of 3.6. That's available from the ringmain. So you've got this nozzle deviation. What's it actually mean? If I click on that, See, I need 65. I'm getting 64.5. And that is a percentage difference. So that's what's meant by nozzle deviation. So you may be willing to accept this. It's up to you. You have the choice. I cannot tell you what to do. Suppose that's 3.2. That's the pressure that's available. No, now the deviation is too much. I need 65. I'm only getting 60.5. And, that's a very significant difference. So I decide that I must do something about it. Now, there are certain tools which are available in PIPENET, which you can consider using. I'm not saying that that is what you should do. My job is to tell you how to do these things. You, as the engineers, you have to agree with your client, or if you're an operating company, you have to make the decision. What am I going to live with? Am I going to go and say we need a bigger fire pump? Or are we going to alter the design and change the pipe diameters? Or am I going to find a way of logically justifying an alternative performance of the system? See here, I can see that is minus 4.1, and that's higher than that, and that's also higher than that. And it may be, you see, that this part of the system, this nozzle, is protecting a particularly hazardous area, and these are not. So it's a bit of an overkill to say that all these nozzles must satisfy the minimum required flow rate. I'll be quite satisfied if this satisfies the minimum flow requirement is satisfied at this nozzle. And I'd like to know what pressure would I need, and is there some way I can get a pressure that satisfies that. See, the pressure there is 3.2 that's available, but there may be a simple way of increasing the pressure the fire pumps generate here. I may want to know what is the minimum. So focus on that, which is nozzle 3. I can say, forget about that most remote nozzle, nozzle 3, that must discharge 65 liters per minute. You see, that's the minimum flow rate. So do the calculation. See, I can't have the pressure defined there as well as the flow rate of this nozzle. Now you can see that critical nozzle is delivering exactly what is required. And then I can see, if I don't do anything at the inlet, I'm going to get 3.2. Is there some way I can get 3.47? Because for the most remote nozzle, I need 4.62. But instead, I can aim to get this pressure, which will make my job a little bit easier. So that's what the nozzle flow rate option is about. There's an option here which says area coverage. In order to activate that, you need to switch to A. what's it actually do? See, how do we work out the minimum flow rate that's required for each nozzle? We calculate the area of the system needs to protect, multiplied by the density and divide by the number of nozzles. We get the minimum flow rate for each nozzle. So instead of saying that I want the minimum flow rate at the most remote nozzle, you could say, I want the total flow rate coming out through the nozzles to be equal to the number of nozzles multiplied by the minimum flow rate for each nozzle. So some nozzles will deliver more, other nozzles will deliver less, but overall, all the nozzles put together will deliver the minimum required flow rate. So that's what this area coverage does. So you can see these two are delivering more. We need 60, 65. These two are delivering more. The other nozzles are delivering less, but the inlet pressure is 3.59, which is a little bit more than what is required for the most remote nozzle option. So that is what it is. Now, it's possible that the pressure here is higher than the required minimum. And let's go back to our most remote nozzle option. Let's say, I'll just make a note of that. Actually, I already got it written down here. So, see, suppose the pressure that's available here is 3 bar more than that. So we can set the pressure there to be 6.672845. So that's the pressure I'm going to set. But of course, having set the pressure, I must not work with most remote nozzle. I should go to user defined. So you can see that the flow rate is 536.3. That's quite a bit more than what we require. We require 394.1. So it's about 142. 142 is about 30 or 40% more than what is required. And if it's a real big system, then you may find that this is highly undesirable because it may necessitate, a bigger fire pump or a bigger tank for storing water. So how are we going to bring it back to exactly the required flow rate? So what I'm going to do now, first of all, is to use the orifice plate method. I'm inserting an orifice plate there. See, I took exactly 3 bar more than the most remote nozzle pressure. See, I'm back to this 394.1. It's 0. So the most remote nozzle condition is satisfied. If I click on the orifice plate, I get an orifice diameter, but I can display this to more decimal places, get an exact orifice diameter here. You already know that the orifice is fixed, so if the pressure changes here, the flow rates will also change. So that's something that we don't want. So one thing we could do is to put an elastomeric valve here. The elastomeric valve is actually a downstream. Don't forget to remove that as input, because otherwise, there'll be flow going in and out of the system. You must make that an internal node. See, it's blue. Click on that. I know that I need 394.1 liters per minute. So the remote nozzle condition is satisfied. The beauty of this is if I make that 8, it still satisfies the most remote nozzle condition. That is the advantage of the elastomeric valve. So the systems, if there are several systems starting, they do not interact with each other. If you allow them to interact, a large system could drain a small system. So a small system does not work. Okay, that's most of what I want to say here, but there is one little feature that I want to show very quickly. And you may actually find that useful. I'm going to import the library. I think this library I just created. No, it's a library I created earlier. It doesn't matter. We've opened a library. Now, what I'm going to do now is to select the pipe type. Input the C factor. So, see, this feature comes under Tools. Even if you don't use auto layout, this would be very useful. For example, I may say, I want 6 nozzles. I must not use the total length. Use step 5. Select nozzle in the library. Just need to give the flow rate. Just say 65. There's also this angle of inclination. I'm going to make it -30. See, I've done that. I can insert. See, I'm showing all these features because they'll be useful for you later on. See, it's blue. I'm going to change that to 2.5. I'm going to copy, paste that. I'm going to create a pipe here. I'm going just say that diameter 80, 8 meters long. See, then what I can do, copy, paste. I must remember to merge the nodes. Copy, paste. And then I can actually do this. I can create that, call that an input node. Input. Maybe you choose the most remote nozzle option. Do the calculation. I've got the inlet. It's giving a negative value because that is on the output node of that pipe. So I can, if I reverse that, you get a positive flow rate. So see how quickly I could create a network. So having done this, of course, you can always modify this if you want. Okay, so that's a shortcut way of creating deluge systems, which might be, and this is also very useful for sprinkler systems. So let's go on to find what ringmains, because we have a lot to cover. Here I will not input the network because you already know how to do that. One methodology I mentioned was to replace the deluge systems by equivalent nozzles. We call them virtual nozzles. See, that's a requirement of 10,000. I don't want to change that because just change the flow rate. GPM. You can see that's too big for a simple nozzle. Put that back. Okay. So these three, by the way, you can also press and hold the control button and select more than one item if you want to. If you're in discussion with some of your colleagues, you can actually select items like this and do the calculation. Let's look at the nozzle deviation. In other words, are the deluge systems getting what they require? And one thing, of course, we know is that this assumes we've got clack valves rather than elastomeric valves, because if it's an elastomeric valve, we would not model that by using a virtual nozzle. I will show you in a minute how you would model an elastomeric valve, because with an elastomeric valve, the flow rate is fixed. So, you know, this is not working properly. I mean, that, for example, we need 1200, we're only getting 10,000, sorry, 12,000, we're only getting 10,620. So let's say these two are helideck monitors, so I want to switch them off because I'm assuming that they will not work at the same time as these three deluge systems. See, it's partially solve the problem, but this is still not flowing enough. So I want to find out what's wrong. Pressure difference. You can see that the pressure difference is very high. You know, that's more than 60 psi. That's too high. And I can look at the velocity. By the way, you also have that little legend you can use, which shows the color coding. You could actually also do print preview and have a drawing like this. And if it's a simple system, you may simply print this out and include this in your report. So you can do things like that. But here you can see that the velocity is very high. You know, this is about 60 feet per second. It's very high indeed. So what am I going to do? It's clear these diameters are too small. Copy, paste, paste. Do the calculation, nozzle deviation, everything is fine. Now, one of the calculations, if you want to see what the pumps are doing, just click on the pump. You'll see where you're operating on the pump curve, the flow rate through each pump, and the hydraulic power consumption, and so on. They're all here. So one of the essential calculations you would do actually is to see what happens if there's only one half of the firewall ring main working. The other half is not working for some reason. I can just go and block that pipe. Need to make sure. Oh dear. See, these are not working properly. Then I see that most of the users are on this side. So maybe I want to move this fire pump to that side. So how am I going to do that? The first thing is I must create a node, right click, insert a node. See, this become blue, meaning it hasn't got the attributes. I can click on it, I can see it doesn't got the attributes. Go there. I'm going to change the length to 12 meters. And I'm going to copy, paste this, and make it 8 meters. The fittings will also be copied. So I need to remove that. And then what I'm going to do, you saw me doing this earlier on. Oops, polygon tool. Right click, copy. See, this area tool or the polygon area tool is very useful for capturing a number of items. And then I can copy and paste. I can move it to this side. And right click. I can rotate by 180. And simply just move it there. must merge these two nodes, and if I want to be perfect, I can move those nodes there. And what about this pump here? See, that's not working. So let's switch off the pump. You can see that it's off, and it's got a dot to indicate it's off. Look at the nozzle deviation. You can see that everything is great. One question people sometimes ask, hey, you've got all these things, and the input node of the pump is the input to the system. I may have a pump. How do I do that? Explode the node. Merge them. Add the pump, and just select the pump curve. As simple as that. You see? So my aim is to show you all these tricks of inserting nodes and copying and pasting subnetworks and things like that. If you know that you can do them, you can use them to your advantage. Let me just check that I've covered all the points. One question that sometimes we get asked is, how do we model a tank? You don't need to model a tank. You can simply input a pipe. This is not an input node anymore. Copy. I can paste it there as well. Pressure. The pressure at the water level in the tank is at the top of the water level is 0. So what I'm going to do now, I must make these internal nodes. I mustn't forget to do that. I'm going to say, maybe that is, make it the same diameter as this one. So it's 200. Millimeters. Now let's say, and this is a key point, and say -15, because that's the height of the water level in the tank. And because it's -15, because the pipe's going down, I'll copy and paste that. Sorry, I should copy the attributes of the pipe. Yeah, I've got that there. So I'll click on that. I can see the flow rate. So let's say that that's the flow rate when the water level is at its maximum value. Let's say that the tank is, let's say the tank is 5 meters tall. So the minimum water level you can allow is 10 meters above this pump. So you've got the flow rate here. The flow rate there, of course, is very high because it's got the pump and also the booster pump. So this is more realistic to look at that. 8503. So what you can do is to take the average and, you know, divide the volume of water in the tank by that, and that'll give you the discharge time or the emptying time of the tank. That's all I want to say. Now let's go on to, you know, time is flying, so let's go on to the more advanced topics. Those of you who are advanced users, I hope you picked up certain things from what I showed so far. So you got these three virtual nozzles there. So the worst case scenario is these three users working. So, you know, I'm the fire engineer working on this, and I've done the basic design. I'm very proud of myself. I'm showing the nozzle deviation. This is approximately 49%, 16%, that's about 16% excess flow. In other words, if I click on that, that's what's required. That's what the pumps are going to generate. The deviation is approximately 16.7% higher than what is required. So I take this to the client, and the client is, and I have a meeting, and the client said, "Whoa, good boy, you've done a good job. Everything is working fine. I've got a little bit in hand. I'm happy with that." And then he says, "Well, I'm interested in looking at the power consumption of the fire pumps. Let's go and have a look at what the fire pumps are doing." You come here and you click on that pump. Well, you know, that shows the power consumption, but you may be interested in, you look at the flow rates and you're both aghast because there are 4 fire pumps working. I mean, that's not right. So your client says, yeah, it's a good design, but you know, you're not supposed to have all 4 fire pumps working. I want you to switch off the electric pumps. And you say, I'm using PIPENET, I can do what I like. Anything you want to see, just tell me. So you switch off the pumps. Flow rate is 4905 and 4904. It's the flow rates are actually significantly more than what they were per pump. And you'll see the pump actually has moved a little bit further to the left. And your client says, okay, this is all very well, but I want to see what the consumers are doing because I need to make sure that they're working fine. Oh, you see, they're working fine. 14, 14, and 46.7. And then your client says to you, you know, you see, this is a way you must carry out the design process because it is not, it's enough in some cases just to do the basic minimum. But isn't it wonderful to look at all the cases that potentially could arise and to show that your network can deal with all of them? And once you've created the network, it's very, very easy to run a new case. So your client says to you, that is a hydrant. I want the hydrant to be working, and also that monitor to be working. I want to consider a case where in reality, when the fire starts, I may have to use a hydrant and a monitor from here to assess these deluge systems. Question is the system going to work fine? Wow, it is great because it's almost 11% more than what is required. So your client is very, very happy indeed. And your client says, listen, I need to make sure that the system would work fine, even if this only one route, or at least if the system is partly blocked. Could be because it's a maintenance engineer who's working on the system and he closes the valve, he forgets to open it. So I use the block command, the block option here, and the system, wow, it's still working fine. This is a great design because even if unforeseen things happen, it's working fine. You can go to the pumps. See, the pump has gone further down its curve because the flow rate is higher, but it's still working fine within its allowed operating range. Okay, now one question that often arises is, I've got a hydrant, for example, or I want to install an additional user. Is there an optimum way in which I can install the additional users? I'll move this a little bit. See, at the moment, these are outputs, but the flow rate is 0. Suppose I want a flow rate of 1300 at 8.5, but I'm writing it down. That is what I get from the deluge system calculation. But how can I design the system in such a way that there is no wastage of water? So I'm going to say the flow rate is 1,300, 1,300, see, I've got 9.85, no, 9.185538 at that moment. I need 8.5, but I've got 9.185538. And here, for 9.176005. The good news is they're both more than the 8.5 I need. But is there a way of restricting the flow to those users? So I take the difference, I'm just doing the sums by hand. Okay, so I need to knock out some pressure. And say 0. That's what I calculated manually. The difference 6,85538. And that orifice plate should drop 0.676. Okay. With any luck, the pressure here should be 8.5. See, look. It's exactly 8.5. So this is how you can balance your system in such a way that you don't get too much flow from the fire pumps. Here the flow rate is only slightly more, but but nevertheless, you may want to make sure that the flow rate is controlled by using an orifice plate. You already know how to use an elastomeric valve, so I will not show that, but I'll show how to use an elastomeric valve in the next example. So I'm going to put those back to 0. Now, next thing I want to show is how to combine subsystems which have been created by, let's say, different fire engineers, or it could be different engineering companies, or it could be an existing system to which you're adding something new. So let's first of all look at the deluge system on its own. That system, I've already done the optimization. See, the most remote nozzle is here. See, that's the most remote nozzle. I click on that. I can see that I'm making note of that. 4.62888 at 4318.5. In other words, that flow rate. In an ideal world, when we combine the system A, there are two steps. One is I want to add this to an existing system and then make sure that it doesn't actually waste water. I want to balance the system. So what I'm going to do, just take this. It's a step you need to follow. I'm going to put it there. I'm going to right click and open another copy of PIPENET. Here, that's the ringmain without the deluge system. See, I'm going to attach the two of them, two identical deluge systems, because that's what you would want to do when you want to build a complete system. So I want to add and attach them to these 2 points and then balance the system. That is my aim. So I go back. First of all, I said balance the system because I set the flow rates to be the flow rates required by the deluge system. Now, first do the calculation. Before copying and pasting, I must do this because the pumps are going to generate 8.73651 and 8.75173. Okay, fortunately, that is higher than the 4.62888 which I need. So let's see how we combine the two systems. That's the first step. I move the system down here, edit, copy. I open the other system, then I activate the area tool, edit, and paste. See, from the schematic overview, you can see that the deluge system has appeared here. So what I'm going to do next is right click, scale to fit, I'm going to take it. Make sure that it's not going to overlap, because if it overlaps this network, then we've got to start again. You can actually right click, paste again. You can do this because it's the same deluge system. It's a good idea to have a look here to see. Okay. Scale to fit. Move the node. And then I must actually make sure they're no longer the output nodes. See, I'm going to do the calculation now. Display options. So you can see this is more or less what we would expect, because it's clear that the pressure that the 5 pumps are generating is higher than the minimum required. The minimum required was 4.62888, but at the 2 points we got something like 8.75 and 8.73. I've written the values down, the pressures, and I've deducted the 4.62888. I'm getting some values here. So what I'm going to do, pick up the orifice plate, place it there, place it there. This orifice plate, don't forget that this plate has got this additional pressure loss in this point. The pressure drop is 4.12295. That one should drop 10768. I hope my arithmetic is correct. If it is, it should be okay. It's 0.16%. That's because the pressure drop in the orifice plate is not exact, but it's good enough for engineering purposes. We need 85, and we're getting 84.9 liters per minute. That's more or less the same. So in this way, we've balanced the system. We've reduced the excess flow rate. If I click on that, I get the orifice diameter. I can display that to more decimal places, and I've got then the orifice plate diameter. But there's a word of warning, caution, and that is, don't take the diameter calculated by PIPENET to be exact, because the formula used in PIPENET comes from the Crane manual, and it's a generic formula. But your orifice plate manufacturer would have more accurate methods of calculating, which depend on the exact design of the orifice plates. It's more reliable to ask them to do the calculation. Okay? This is mainly to give you an order of magnitude feasibility that you can use an orifice plate to do the design. Now, see, let's have a look to see how we would use. Oh, let's take this one more calculation. 4.12295. It's fine. Now suppose, see, this is yet another new thing that you can learn. I'm going to choose a polygon tool. Press and hold the shift button, click, 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 click. I'm capturing that area. I can right click, turn nozzles on. So you can turn on all the nozzles within that area. Want to see? See now the worst nozzle here is delivering 10% less than what is required. So apart from the fact that the orifice plates are not recommended, it also is not an ideal way to balance the system, because it doesn't stop systems interacting with each other. So let's go and capture that area again, right click and switch them off as before. But I want to use an elastomeric valve here rather than an orifice plate. So what I'm going to do, right click. Well, what I'll do for ease, I'll just explode this node. Strictly speaking, you should break the pipe by inserting a nozzle, node and so on. To save time, I will simply explode two nodes. So we know that the flow rate we need for the optimum performance of the deluge system is 4318.5. I can right click, copy, paste, because there are identical deluge systems. And see, that is exactly what we need. We go here, it's the same as what we need. Let's do the exact same thing as before. Choose the polygon area tool, press the hold the shift button, click, 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 click. Capture the whole area, right click, turn nozzles on. Nozzle deviation, you see, it doesn't starve the, in other words, another system starting up somewhere else, it doesn't drain these two deluge systems. So as long as the pressure that's available is higher than the minimum inlet pressure at the elastomeric valve, the system is going to work fine. Okay, so I think this is all I wanted to show. Let me just have a quick look. There's something else that may be interesting for you. This is just a feature so I can start, click on that, press and hold the control button. Sorry, I don't mean that. Press and hold the control button. You can make a path. And I go to, see there is this tab graphs. If I click on that, it'll show me how the pressure changes. The pressure seems to change very quickly here. I right click 457 and 460. I can actually display that's not very good. So what I can do, I can say 457. I can use the search tool. So it's telling me that there's a sudden pressure drop somewhere in that part of the system. Okay, so I can then investigate to see what if anything, I can do about it. So that's creating a path. Now, I said to you that when it comes to offshore systems, there are certain calculations you can do which you wouldn't typically do with onshore systems, and that is using the break option. So I'll take the case here. It's an offshore firewall system. You see, this deluge system here is the focus of my attention. It's actually delivering much more than what is required. But anyway, that's a different question. We can optimize this and so on. But the question I'm going to ask is the following. And these are this idea, by the way, was introduced by Brown and Root, as it used to be. Now it's called KBR. It's part of KBR. But before the KBR days, there was a company called Brown and Root. They did some fantastic engineering. And, you know, this is part of the unfolding story, because once you've got this network, you can do all kinds of calculations very quickly. Your client is very interested to know what is going to happen if there is an accident here, and because of that, a pipe gets broken. Because in his mind, what he's thinking, two things. One is, if water is gushing out from here, you see, you've still got enough static head here to create some pressure in this part of the system. Furthermore, typically, the pipes which are here are smaller diameter than the pipes at the lower part of the system. So the effect of a pipe rupturing here may not be as bad as you might think when you consider a system at the low level of your platform, in this case, a platform complex. So let's consider two cases. One is where the pipe breaks at a low level. See, we're considering the pipe breaking here. You can see that it's breaking at a low level. It's clear that if a pipe breaks here, what's downstream is not going to work. So let's forget about it. But some reason we are assuming that the pipe is breaking here, and at the same time, our focus of attention is this system here. I'm going to maximize it. So to do that, you see, there is, if you look at a pipe, there are actually three options: normal, blocked, and broken. Broken here is not really accurate. It's to give you an idea. To do the calculation accurately, to look at it quantitatively, we should take a different approach. Why? Because if a pipe actually breaks, the position of the break is significant, because if the pipe breaks at this end, it'll behave differently from the pipe breaking at the other end. So you see, so this pipe, we inserted a node, broke the node, and then you define the position of these two nodes. And you simply set the pressure to be 0. The pipe is completely broken off. The pressure will go to 0. So I'm going to do the calculation. Click on that node. We're getting a very, very big flow rate, as you would expect. And if you go to this system here, look at the nozzle deviation. You see, previously the deviation was of the order of plus 50, but look what's happened. It's some of them are negative. In other words, they're not delivering the required flow rate. Now let's consider a case where this pipe here, which is close to the heli deck, is broken. In fact, the pipe is more likely to rupture in a place like this. It's the same, we subdivide the pipe and set the pressure there to 0 and 0. See here, we're not creating an isolated network, so there'll be flow rates going through both parts, both halves of the system. You can see that's negative. What does it mean? If I click on the arrow, see I drew the pipe that way, the flow rate is going in the opposite direction. That's what minus means, and that's positive. So you can see that quite a big flow rate is going out here. But is the static head enough to make the system work properly? So wow, that's fantastic, isn't it? Although the pipe at the top is completely broken, the system is working fine. This is the type of calculation which Brown and Root did 30 years ago. And, you know, their customers love them for it because it unfolds the story. What happens, you know, if there is a disaster? Will the system still work, and is it not going to work? Okay, so that is what I want to show, but by way of advanced features. There's just one thing I wanted to mention, which I promised I will show you, and that is, what is the logic behind using these virtual nozzles when you have clack valves? Clack valves, for those of you from the US, they are open-close deluge valves, and colloquially they're called clack valves. They're not the same as elastomeric valves, which control the pressure. They are open-close valves. What is the logic behind using virtual nozzles when you've got clack valves? So let's look at this. Let's take a very, very simple deluge system. Look at the elevation first. It's flat. The elevation everywhere is 0. and the pressure there is set to 4. And of course, the spec is user defined. Do the calculation. I get 621.6. That's the flow rate. Now, you see the K factor equivalent to this. In fact, PIPENET will give you the value. Let's take that one. See, I'm using a beta version of the latest program we have. See, 621. But PIPENET itself gives you the equivalent K factor, 310.81. If the K factor method or the virtual nozzle method has merit, then you see the K factor 310.8 times the square. If I change the pressure here to 8 bar, the flow rate will be 8, the square root of 8 multiplied by 310.8. So you will get 879. With 4 bar, we're getting 621.6. If we increase the pressure to 8 bar, we get 879.07 using the virtual nozzle method. So I'm not doing any PIPENET calculation. So let's see what happens if I change the inlet pressure. Sorry, if you, I'll keep that around here somewhere. Change the inlet pressure to 8. See, it gets 879.3. See, the K factor method gives us 879.07. It's a very good match, I would say, because of the numerical, the differences because of the numerical aspects of the calculation. See, this is and changing from 4 bar to 8 bar, doubling the pressure is actually quite a big change. And the K factor method works in this case. Let's consider another case, which is like this. So if we look at the elevation now, see, all the nozzles are 5 meters above the input. So, you know, this will make a difference of approximately half a bar or 7.5 PSI, something like that. And let's see what happens. Of course, we would expect the flow rate to be a little bit less. It was 621.6, but because the elevation change is only 582.3. I'll make a note of that. And then you see the K factor, I calculated it here corresponding to that. In other words, dividing by the square root of 4 will be simply half of that, which is 291.15. That's the equivalent K factor. So let me do the calculation, same calculation. It's 291.15. That is the equivalent K factor. I put it here somewhere. 8 square root of that multiplied by, I get 823.49. Now what happens, that is using the K-factor method. But let's increase the pressure to 8 and do a rigorous explicit calculation. $851.9. See, the K factor gives 823.5. The rigorous calculation gives us 851.9. Now, you know, this is not terrible considering that we've doubled the pressure, but still there is a difference. So what is causing this difference? See, one thing that we pay a lot of attention to detail. You know, in PIPENET, the friction loss column is separate from the static head loss column. Why are they separated? Because if you have a system and if there is a static head change, usually there's nothing you can do about it. But the friction loss is something that you can change by adjusting the diameter or whatever. So that is more within your control than the static head loss. That's why PIPENET separates the two. But the important thing here, so you can see, there's a half a bar. That's about 7.5 psi pressure drop because of that static head in some of the pipes. Now, that does not change with the flow rate. Only the friction loss changes with the flow rate. So when we increased the inlet pressure to 8 bar, double the inlet pressure, the static head loss still remained the same. And that is, you know, and there's an underlying assumption that if you use the K-factor method, the relationship between the flow rate and the pressure is quadratic. And that assumption is not valid if the static head is significant. In many, many cases, this will not matter, but if you have something like a deluge system going down the leg of a platform or something like that, where the static head is significant, then you've got to be cautious in interpreting the results with the equivalent virtual nozzle principle. Now, that's all I wanted to say today. It's wonderful to see you all. Thank you very much for being here. And if you have any questions and which were not answered here, you can. Victoria will repeat this. I'm just putting it in writing and also showing how to input a text. So if you have any questions, they've not been answered during the webinar, please raise the questions using that email address. Okay. So I'll hand you back to Victoria. Victoria, you here?
Thank you, Sebastian. Thank you very much for delivering the session, and thank you for all the attendees for still being here. We understand that we took a little bit more than 2 hours, so thank you very much for staying with us. Sebastian, could you please mute your microphone? Thank you. Okay, as I promised, we will share the video recording of today's session later this week. Also, if you are an existing customer and if you have a valid license for PIPENET spray sprinkler module, we will be happy to share the actual files which we used, and you can practice with them and play around with the examples that you saw today. The email address which you see, support@sunrisesys.com, that is the email address of our support line. And if you're an existing customer and if you have any technical question, please write to this email address. If you are not a customer yet and if you have any questions, please write to me or write to our general pipenet@sunrises.com email address, and we will be happy to answer all your questions and provide you with more information about PIPENET. If you would like to receive a certificate of attendance for today's session, please write to me. You have my email address, I believe, and I'll be very happy to send you a certificate of attendance. Now, thank you very much for staying with us. We are planning to have many more webinars this year, so please follow our announcements, and we will be happy to see you at our future events. Again, if you have any questions, do not hesitate to send us an email. Thank you to all my colleagues who stayed with us and who answered the questions in the chat. And have a good day, and we look forward to hearing from you and seeing you at our future events. Thank you. Bye-bye.